Hello, welcome to Space Store Live. Thank you for joining us if you're joining us on YouTube. If you're tuning in later on Catch Up, thank you for watching. Today we're back with the very first talk on Space Store Live Thursday night of 2021. And we've got a very special person in the house, David Homfray. Hi, David. How are you doing?
How's it going? I won't go so far to say special, but thank you very much.
Awesome. Thank you so much for joining us. Now, those of you who don't know David, he's got a background in something really, really cool. It's fusion and space research. And he's got a number of accolades. I'll get started. He's a chartered physicist, a chartered engineer, and he's a fellow of the Institute of Physics, the Royal Astronomical Society, and British Interplanetary Society. So we've got loads of things to talk about. But what's tonight going to be about, David?
Yeah, so we just really want to discuss how important power is in space if we want to become a spacefaring species. Look at a little bit of what we do now and how the cost of launch, because it's reduced, the potential is in the future.
Awesome. Now, just a note to our audience, if you're joining us live, make sure you use the YouTube comments or chat feature to send us questions in throughout the talk. And hopefully in around 40 minutes, we'll be having a live Q&A session with David, which I'm super excited for. So I'll leave the floor to you, David. I hope you guys enjoy the presentation and remember to ask questions throughout.
Well, thank you very much. Let's just bring this up. That good?
That's awesome.
Okay. Well, thank you very much for inviting me to talk this evening at Space Store Live. As my name's David Homfray. Just to give you a little bit of a summary of, let's try that again. Just to give you a little bit of a summary of what I intend to talk about this evening is on the subject of space power. I want to give a little bit of context of first of all a bit about why I'm talking about this, look at what we have done in the past in terms of space power, why it's so critical, look at what we're currently doing, and then really start to explain why I think power is the critical aspect if we want to become a spacefaring species. Look at some of that current research that's been enabled by low cost of launch now, and some of those future technologies and the missions that they may enable. A quick shout out to Tim Tinsley from National Nuclear Laboratory and some of the nuclear power supply. I've robbed him awfully, so I'd like to give him a quick shout out. So just to give you a little background of myself, I'm a massive geek and I love all things big science and big engineering. So I've been very fortunate in my career to spend most of my time thinking about what the future looks like, trying to split it up into little chunks, manageable chunks, and seeing where I can make value out of those chunks at the moment. And I started my career in functional brain imaging and then spent the majority of my career in fusion research, trying to recreate the same conditions that happen in the sun. And now I'm working at the Satellite Application Catapult, looking at upstream and downstream technologies. So, but the burning issue that's always moved me in my career is this idea of this finite planet with finite resources. And so the two aspects I think that will allow us to be more sustainable on this planet is the idea that we have higher energy density that will allow us to look at how we use our resources on this planet, but also to leave the cradle, as Tsiolkovsky put it, one of our founding fathers of rocketry, to leave the cradle and to try and get resources from off planet. And so my journey in space energy was about 5 or 6 years ago, where I was doing a part-time master's, and in that master's I was trying to design a thruster. And every time I did the calculations, it was like, oh, if only I had another few kilowatts. What happens if I had a megawatt? Okay. And so in the end, it was like, right, I'm going to throw the thruster away and I'm going to think about the power supply. So I'm a big sci-fi fan, so I thought I'd put this all in context of some movies. So if you want to get around space quickly, so space is really big. To get around space quickly, to reduce the time of flight, you need more power. The more power you have, the faster you can send your propellant out of the back and the quicker you can move your spaceship. In the bottom left-hand side, you can see the Martian, and he's unbelievably cold, and space is either really cold, really hot. It's always trying to kill you, and therefore having high energy density and lots of power enables you to build that environment which can protect you, either your astronaut, or can protect your spacecraft. So I'm explaining that power is really important, but also mass is really important. So when you launch, every kilogram costs so many $1,000s. So in the end, I'm going to start talking about a thing called specific power. So power's not just, power is important, but specific power, how many watts can I get out of my kilogram of power supply? That's really important. And we've been concerned about power from the very first launch of Sputnik all the way to 2024, 2025, when we're thinking about putting people back on the moon, and even further. There will be concerns about how you design your spacecraft and how much power those spacecraft need. So power in space, you've only got a few options, and I'm putting up here the pictures of the Apollo missions, because they pretty much use every different type of power supply you can imagine. So the majority of spacecraft that are in low Earth orbit, in geosynchronous orbit, they use solar, and actually most spacecraft use solar power. And you can see in the top right hand picture, you can see Buzz Aldrin. That is a small experiment using solar power to look at some of the issues on the moon, whether it is to measure distance, to measure if there's any movement, if there's any geological movement, what's happening on the surface of the moon. There's of course chemistry, and if you look at whether you're launching a space rocket or whether you're looking at the lunar module, those rockets use chemistry and the power within that chemistry. You have things like energy storage. That could be chemistry, like fuel cells used on the space shuttle, or batteries used in the lunar rover. And then you've also got nuclear. Now, with my nuclear background, I will highlight nuclear throughout this talk, because actually it is the area where I think you can get the highest specific power, and it's the most likely to enable us to become a spacefaring species. So in the bottom right hand side, you can see Alan Bean taking out actually a canister of plutonium, which was used in a experiment called ALSEP, which was monitoring the lunar landing site for over a year. And then there's mechanical. Now, I'll just show you this because it wasn't used on the Apollo, but technically this is the NASA G2 flywheel. And what it does is you spin it up. There's energy in that rotational, in that mass that's rotating. And then when you need it, you change that mechanical energy back into electrical. And then, of course, you can combine all of these different power supplies in order to enable a mission. So let's start on energy storage. So they are combined, that you can have either a primary battery or a secondary. Now, the primary batteries are, you can't recharge, and they're traditionally used in space to be deployed on small missions, such as probes being carried by a larger parent spacecraft. So they can be dormant for years while they're traveling to whichever planet they're going to, and then they have to be woken up in some format, and then you have a specific lifetime of that battery. Now, they're actually quite a good power density to them. So you can actually, if you look at the lithium sulfur dioxide, you can actually get like 350 watt hours per kilogram out of them. So they're quite good, and they have relatively good storage life. However, they can't be recharged. Now, and you've also then got the secondary storage. These are generally combined with, for instance, solar. They don't have particularly good specific powers, and you need to think about how big they need to be, because you can't discharge them fully. You the more you cycle the batteries, the less you need to discharge it. And so if you want to discharge it fully, you might only get 1,000 cycles of the battery. But if you were only to discharge it by 20%, for instance, you could get 10,000 cycles out of it. So it's that balance between how long do I need my spacecraft working for. And also another thing that was used primarily, again, I've already said, but on the space shuttle are fuel cells. They're relatively good in terms of specific power, but one of the real benefits of them is technically you can use your propellant and your air supply as the chemistry, the energy that you use to create your current. So this is one of the missions using primary energy storage. It was the Huygens probe, part of the Cassini-Huygens mission. It successfully landed on the Saturn's moon of Titan in 2005, and it had 5 of these lithium sulfur dioxide batteries. One of the amazing bits that the European Space Agency had to deal with is, as the Cassini-Huygens was traveling towards Saturn, there was a bit where the European Space Agency had to wake up this probe, and hopefully everything was back and everything was working. But it was incredibly successful. It allowed us to see amazing detail on Titan, and it also proved that there must have been liquid methane. And just to kind of show you the kind of pictures that it took, and you know, this is 10 AU away. It's amazing to see this. But so that's on the energy storage. And there's so many issues with energy storage. Primary, obviously you can use it once and it's always depleting. And secondary, you need something else. And solar is that something else for most of the things that we know of as spacecraft, whether it is low Earth orbit, Earth observation, comm satellites in geostationary, whether it is in the top right hand corner, you've got the Soyuz spacecraft, all using solar. You obviously have an efficiency that solar can provide. So actually at the beginning of life, solar can be around 25% efficient. But of course, it starts to degrade over time. So you also have an end of life of solar, where after 15 years, it can move from, say, 200 watts per square meter of solar panel to down to 180. And when you're designing spacecraft, you really need to be aware of, again, what is my operational life of my spacecraft? how long do I want to charge my battery, what's my day night time, and it can be quite complex. Now, solar will be used both on spacecraft, but it also for our exploration missions to the moon and Mars. And because sometimes either a spacecraft in low Earth orbit goes into the Earth's shadow, or you're in a big crater on the moon, for instance, now you need to start combining it with secondary storage. And so give you a mission which is predominantly solar, and of course this is really close to the sun, is an amazing mission by the European Space Agency called the Solar Orbiter. This spacecraft is really looking at the sun's magnetic field and the solar wind. It's trying to get understanding of how those things, the mechanism, how they affect the rest of the solar system. It's a really amazing spacecraft, but the solar panels themselves, because they're so close to the sun, these are not like solar panels you would have on your roof, for instance, because the amount of watts per square meter of these solar panels are significantly more than you would find as you get closer to Earth. But again, this has been going, it's a relatively recent spacecraft, but already taking amazing images and doing an amazing experiments to look at how the magnetic fields and the solar wind affects the rest of the solar system. It's really quite amazing. So we've looked at the Huygens, we've looked at the solar orbiter, but it's a real pain in the backside trying to calculate these things. And just to give you a really quick example of, let's think about a low Earth orbit Earth observation satellite, and trying to work out how do I power this spacecraft. So I think about having a combination of solar and batteries. I know how much power my spacecraft needs, how much power my payload needs. I also understand the orbit that this spacecraft's in. So I understand what my minimum day is and my maximum night. So let's consider first, we're in the shadow, so no solar, and we've just got the battery. So we know that we need to power the payload, we need to power the spacecraft. But my discharge efficiency of my battery, there is an efficiency loss there. So I need my battery a bit bigger. Now, I've already explained that I can't discharge my battery 100%. So maybe I can only do it for 20% in order to maximize the life of this spacecraft. So again, my battery gets bigger. I then need to down select the type of battery. And again, now I start to understand the mass, all impacting on what this spacecraft does. So now I consider being in the sun. Now my solar panels not only need to power my spacecraft and the payload, but they need to charge the batteries. And to charge the batteries, there's an inefficiency. So my panels need to be a bit bigger. My orbit will mean that my solar panels are in a slight inclination. So I will have an inefficiency there. So again, my panels are bigger. All of those panels are not just solar cells, they're interconnecting those solar cells. So 30% of a solar panel is interconnects. So again, my solar panels are bigger. And there will be a degradation. So I need to make sure when I design my spacecraft, I'm thinking at the end of life. So again, my panels get bigger. So I'm getting bigger batteries, bigger panels, and I'm starting to now impact on the size of my payload. And of course, there's operating temperatures. There's all these different things that mean it's really difficult to try and calculate this spacecraft power. Now in solar, one of the obviously main issues is as you start to move away from the sun, your mean solar irradiance starts to reduce. At the Earth, it's around about 1,400 watts per square meter. But as you start to move to Saturn, which is 10 times the distance from the sun to the Earth, Saturn is 10 AU, then all of a sudden you get to the point where you're actually only probably 50 watts per square meter. And that means that your panel sizes become really, really large and unwieldy, difficult to launch. And you really need to start considering your payload size. So this is where we start to think, what other power supplies could we use when we don't have enough irradiance from the sun? And that's where nuclear comes in. This is my favorite spacecraft. It's Voyager. The banner at the bottom gives you the real-time information of Voyager, and I think this was on Sunday, and it's 152 AU away. So light coming from Voyager takes 21 hours to get to the Earth. It's an incredible craft. Launched in 1977, and the reason why it's still doing things is because it has a nuclear core, a nuclear power supply. Now, nuclear is obviously expensive. There are challenges in terms of launch, but it gives you a truly independent supply. It is independent of orbits. It's independent of the location in the solar system. It's proven it will just work. And you start to get good power density. Now, to try and give you some understanding of why it's so good is if you look at fossil fuels and then you take fission, it's 6 orders of magnitude better in terms of joules per gram of fuel. And so that's why it's so exciting to think about nuclear as a method of powering spacecraft. There are a number of types of nuclear spacecraft, nuclear power supply, all the way to minuscule beta voltaic batteries. So they can be sub-watt, but they can last hundreds of years. So to keep things slightly powered. You have things called radioisotope heating units. Now, these are not providing power as such. They're just keeping important electronics warm. You've got radioisotope power systems. The most famous of those are a series of things called radioisotope thermal electric generators. So this is a little ball of nuclear fuel that is warm, and you change that heat into electrical, and you do that by using some form of semiconductor. But of course, now you can start thinking, if you're in that kind of frame of mind of, can I build fission reactors in space? And with my fusion background, can I build fusion reactors in space? And that's where you start to think about the various aspects of, what am I trying to power here? Is this something where I want to move humans really quickly to the planets? Do I want to move massive payloads in robotic missions? And this starts to give you flexibility in making your power design decisions. And I've already mentioned a number of spacecraft that actually already have flown using small nuclear power supplies. Voyager and Voyager 1 and Voyager 2 have used RTGs. I've mentioned that the Apollo missions had RTGs as well in them. I've mentioned the Huygens probe. The parent spacecraft Cassini had 3 RTGs in it. That was launched in '97. New Horizons, that took such amazing pictures of Pluto as it as it moved outside out of the solar system. There's some lovely picture on the bottom right. It used an RTG, a spare one, which was available from Cassini-Huygens, and MSL, which is the rover on Mars, also has an RTG, and currently the second MSL is in transit, and I think it should be landing in February. So again, really exciting, but powered RTGs. And one of the problems with some of the previous rovers that were using solar is they got dust on top of them, and so they almost needed to wait a while until they had more favorable conditions, and some of that dust that covered this, the solar panels were removed to give it enough juice to carry on going. There has been reactors in space. So the picture in the center there is the SNAP 10A. It's the only US reactor sent into space. It was about 0.5 kilowatt, and the Russians have sent in 30 odd reactors. Now this, so 0.5 kilowatt is quite a lot of power when you consider what normal payloads and normal spacecraft have. And this really opens that opportunity up. Similarly, they've also looked at, instead of changing to electricity, can we use the thermal properties of the reactor to actually build a propulsion device with the reactor built in? And this is the Nerva engine. It was never flown in the end, but it was bench tested very successfully, where in the center of that engine is a nuclear reactor. Your propellant gets incredibly heated as it passes through that reactor, and then it's passed through a nozzle, and it works just like any other thruster. It just so happens to be heated using a nuclear reactor. Again, this is another way that I see nuclear going forward, and I think nuclear thermal will be just as important as nuclear electrical. So what's changed now? So why am I so excited about this new phase, and why do I think now is somewhere where we can actually truly start thinking about becoming a spacefaring species? And that is because we have now started to get reusable launch vehicles, and actually the cost of launching things has decreased significantly. When you look in the left hand side, the space shuttle, it's a wonderful spacecraft, although in my opinion, and this might annoy a lot of people, I think it fundamentally stifled us, because it was just so expensive to develop, and it was every kilogram launched on the space shuttle was $65,000. That's an incredible amount of money for what is just a bag of sugar. Now on the right hand side, you can see the Falcon Heavy. And not only is the cost of the development of that rocket a lot lower, the cost of launch of payloads within that is really low, $2,300. And Elon Musk wants to go even further in Starship, where finally we as a species can break that $1,000 per kilogram mark. And if he can really do that, that is an amazing thing for us as a whole species. It means we can design spacecraft, we can build up in orbit, and we can think of new mission architectures nobody would have done even 5-10 years ago. So it's a really exciting time. So how do we become, I can get stuff into space. So how do we become a spacefaring species? And from the title of this presentation, you won't be surprised to hear that I think it's power. So all the interesting stuff is far away. So we need to reduce the time of flight. We need to do that with astronauts on board, both for the physiology and the psychology of spending large amounts of time away from the Earth. And to move a large spacecraft around, you only really have two variables. You can either throw a lot of propellant out of the back of your rocket, and that's not favorable, because the more propellant you throw out the back, the more propellant you need. And then you start to decrease the size of your payload. It's far better to have a really high exhaust velocity. So instead of throwing lots of stuff out, you throw that stuff out at really high speed. And so if you look at chemistry, so the way that we launch rockets from the Earth, or the Apollo mission, the majority was using chemistry. But those chemical rockets are energy limited. So you can only get to a certain exhaust velocity. So you start to look at electric propulsion or thermal propulsion. And solar, radioisotope thermoelectric generators, and fission have pros and cons to them all, but in the end, fission and fusion are likely to give you the megawatts you need for real exploration. And in my opinion, if you want real interplanetary travel, you need to get above around 1 kilowatt per kilogram. And that becomes some very advanced fission concepts, or you start to move to fusion designs. And so really that's why nuclear enables you to become a spacefaring species. And so for me, when you're looking at the propulsion options, whether it's a robotic mission, you can, if you're looking for Mars, maybe even Jupiter, you're starting to look at tens of kilowatts might get you to Jupiter. If you want to get a little bit further, you really want to start looking at the megawatts. But if you start wanting to move people to distances of around 10 AU, you need tens, if not hundreds of megawatts. And that's absolutely vital in order to get people without spending too long in space. So what are we doing? How are we achieving this? What I am extremely proud of is both in the UK, we have a really proud heritage of working with nuclear, and internationally there's lots of work going on. So in terms of radioisotope thermoelectric generators, the University of Leicester are the absolute don at this. They are brilliant. So one of the really clever things they are doing is all the radioisotope thermoelectric generators produced so far have used plutonium. But actually, it's really difficult to obtain plutonium. We're not creating the weapons that we did, thankfully, like we did in the 60s, 70s. And so actually plutonium-238 is quite difficult to obtain. Americium is a material that we actually have to store in the UK in places like Sellafield. We have quite a lot of americium. It doesn't have quite the same specific power as plutonium. However, it's available, it's cheap, and we can take something that we spend money to look after, we can sell that product to send spacecraft into space. And so currently the University of Leicester, Airbus, and the people you see in the banner below are working on, they're starting on prototypes, quite small at the moment, around 10 watts, but they really want to start looking at how to get towards that kilowatt. And so it's a really exciting UK product where the UK could produce RTGs for America and for the other nations and ourselves. This came out only last week, actually, which was quite fortuitous. So UK Space Agency and Rolls-Royce have got a study into nuclear powered space exploration. They are looking at the hundreds of kilowatts to almost megawatt scale, very much built on Rolls-Royce's nuclear heritage. Rolls-Royce want to do it because they see a market there, and because they also see that the research that they do to try and make a nuclear reactor in space will make it more compact, will make it more safe, and therefore they might be able to get value from terrestrial applications as well. And it's incredibly exciting that a large organization is now looking at how they can get involved in making and enabling large spacecraft in space. And again, this is amazing, came out last week. The National Nuclear Laboratories did some really exciting studies and did some preparation for real demonstrators for a EU-funded project called MEGAHIT, and then followed on by DEMOCRITOS. It was quite an international partnership, and it looked at every single element of a spacecraft that was needed to be able to produce a 1 megawatt spacecraft with all of its propulsion, propellant, thrusters, payload, the shielding requirements. And what they showed was, by getting a very high operating temperature in the power conversion, you could get quite efficient spacecraft. As you get to higher operating temperatures for your, so when I create thermal power from my reactor, I need some form of primary coolant to suck up that heat, and then I use that in some thermal to electrical cycle to create the electricity. The hotter I can go with that primary coolant, the more efficient the cycle is, but also the waste heat is at a higher level, and you actually means that your radiator sizes is reduced significantly. So their operating temperature was very high at around 1300 Kelvin. So National Nuclear Laboratory did all the technology and all the nuclear safety on that, and it was a really exciting design, and it showed that you can use near-term technology to make significant spacecraft. And by the way, it's a cool looking spacecraft. NASA are also doing some work on a thing called KILOPOWER. This is where they want to use plutonium-238 to create around about 10 to 40 kilowatts of power. In the bottom right hand side, you can see an actual prototype that they've built, and this is to provide surface power, not necessarily for propulsion, but something where you can move to Mars, you can put it on the moon, and it gives your base a stable power. You can see this a disc on the top, and that's a radiator, and then it uses Stirling power conversion to take the heat and to create electricity. Now, they've started that design around 10 kilowatts, but they really have this program where they want to push it to really increase the kilowatts per kilogram. So lower launch masses for the same sorts of power. So again, a really incredibly exciting. Demonstrators have been done, and there's discussion that they want to include this in their Artemis program. The Artemis program is their encompassing program for the moon missions. It includes their Orion spacecraft. It includes the Lunar Gateway, which is a space station which will in a lunar orbit, and they are discussing now including KILOPOWER in there. And then finally, the work I've done. So I'm not happy with just megawatts. I want gigawatts of power. And so I did a study with my background in fusion, looking at whether I could take terrestrial fusion designs and whether I could reduce the mass on them to try and get over that magical 1 kilowatt per kilogram. Because these machines are very high temperature, so the plasma in the center can be up to 180 million degrees C. Because it's throwing out a lot of neutrons, maintenance becomes very important. So in my design, I had to balance the amount of power it produced versus how many times over the years do I have to perform maintenance on this. Looking at the terrestrial designs, I reduced mass wherever, got rid of the vacuum vessel, let's use space to do that. I've already talked about the primary working fluids previously, but I looked at where I could combine the biological shield with the primary working fluid using a really cool material called lithium hydride, running it at really high operating temperatures, just like MEGAHIT did at around 1300 Kelvin. And because the fusion power density is proportional to the magnetic field of this magnetic bottle, which is the fusion device, I ran at ridiculously high magnetic fields, around 22 Tesla. And from that, I showed that it was feasible to get a power supply which was around 1.5 kilowatts per kilogram. And what that really means in real terms is I could send a 700-ton spacecraft around 4 AU in around 400 days. So I could deliver hundreds of tons of payload to Jovian orbits. And so now you're starting to open up all these different mission architectures and really enables you to go, what would we like to do in the solar system? And now I'm taking this design further. I'm working with the British Interplanetary Society, and I lead one of their technical working groups, which is trying to push this a bit forward. And if you've not heard of the British Interplanetary Society, it's an amazing bunch of people, and I can't recommend that society enough. They've really given me, throughout my career, they've been massively influential. So one of the other roles at my at the Satellite Application Catapult is the use of space power, not for spacecraft, but actually for use in terrestrial, the power grid. So currently I'm helping to look at designs for space-based solar power. This is because of the day to night cycle, because actually you lose a lot of power going through the atmosphere. So in space, in low Earth orbit, it's around 1400 kilowatts per square meter. But when you start to get to the Earth's surface, it gets to around 800 watts to about 1000 watts per square meter. If you're able to change the way that power goes through the atmosphere, you really can enable 24/7 high throughput, 2 gigawatts of solar power coming from space. The spacecraft themselves are quite large. However, we have already mentioned cost of launch is reducing. We are doing more work in in-service maintenance, manufacture, and orbit. And so these spacecraft are now going from sci-fi to seriously organizations thinking about how you would do it. And again, UK government has commissioned some new research, and we are looking at how you could do this to meet net zero targets by 2040, 2050. So I'm going to finish there. I hope that it's been a bit of a whistle-stop tour, but I would hope that I've convinced you that power is a really critical design parameter in anything you design in your spacecraft, that it's not just power that's important, it's specific power. And that is what's really, you really need to increase both of those if you want to become a spacefaring species. All these cool designs are enabled by our reduction in the cost of launch and the cost per kilogram of launch. That nuclear has massive potential in the future, and that there's some really cool projects going on now, both nationally in the UK and internationally. And so, yeah, I'd like to conclude there. Thank you.
Awesome. Thank you.
Oh, and in 45 minutes on the dot, I think.
Yeah, you finished bang on time. Thank you so much for such an incredible presentation. I hope everyone tuning in really enjoyed that. Once again, if you have any questions, let us know in the comments below. We're going to be live for another 10-15 minutes, just talking with David about his background. So yeah, thank you so much, David.
Shall I stop sharing?
Yeah, you can stop sharing. Great, thank you so much. I learned so many new things about power that I didn't know before. How did you get involved in, like, what made you interested in power, and not even kilowatts and megawatts? We're talking about gigawatts of power here. Like, what makes you interested in it?
So again, it's just this background. Very early on, I need to learn. I'm always reading and very interested in stuff. I'm hungry to learn, and for me, the background I had in fusion, when I went to I remember at school somebody coming along and mentioning this new experiment called the Joint European Torus, this new fusion reactor that's coming online, and I was so excited about this big project that I went to do physics, I went to do engineering. Unfortunately, I was then able to go and work on that actual machine. I found out the person that gave that talk was an engineer in charge of JET, and I became an engineer in charge of JET. And I think that the processes that we utilize every day in terms of making products have always been taken for minimizing energy. And once you have high energy density, you can think of methods that are the most sustainable for resource rather than just energy. And as soon as I got that into my head, then energy was the thing I needed to get into. But always interested in spacecraft. So when I had the opportunity to combine the two together, it was like, right, I've found where I might be able to have my niche.
Awesome. And then I know you mentioned that you've got a physics background, you've done some theoretical physics, and then you've got an engineering background. Like, in your day-to-day role, I know you've recently joined the Satellite Applications Catapult based in Harwell. How do you strike the balance between being a physicist and an engineer at the same time?
Yeah, so by the way, just to say, I was never good enough to be a theoretical physicist. I was always an applied physicist. So okay. I was always trying to see how I could actively build that experiment. So I'm interested in a phenomena. I want to either measure it or utilize it. So how do I go about that? And so my first job at the University of Oxford, I would consider myself as almost like a physicist janitor. So one day I could be building a shed or changing a light bulb in the toilet, but the next day I could be building a coil for an MRI scanner or writing a science paper. And that job was so massively influential for me. So it allowed me to think about how to do research, how to set out an experiment, but also gave me those practical lessons of, okay, it's not good enough just to think it. Now I need to build this thing.
Yeah.
So when I moved to Fusion, I had started to learn how to do software. I had already had a little bit of a background in building circuitry, building bits of computers, learning how to build the experimental devices that would take the signals. And so it's just this natural progression of, I know what I want to do. I want now to go and build this thing myself. And so I'm a builder.
Yeah.
So you know, when you go on a course, they say what your profession is. So I take it in turns. I either write rocket scientist or I write builder on it. And I always take that in turns.
That's great. Just a question like that I think a lot of young scientists or engineers I think might relate to is during school, we're always taught about theories that exist. Like this is, I don't know, E equals MC squared. You're taught equations and you're taught theories and you're taught rules of this is how science works and how fusion works and how fission works and what's the differences. And university, I think, is pretty similar to school in that sense, where you still learn about theories and you learn about what people have done in the past. You do a few experiments to prove that they were right. Whereas when you move into industry and when you're doing like groundbreaking research, as people in your industry are doing and you are doing, then where does the line come where you're like, okay, you're actually making new technology, and how does that feel?
So it's incredibly exciting. So again, you know, whether it is nuclear power in space, whether it is space-based solar, again, I was very fortunate, my career at UKAEA, looking at how we commercialize a fusion reactor. What does 2040 look like? It's incredibly exciting, but I think it's not so much about education. Is obviously important, but it's about a passion for learning. So it's the idea that we all learn at different times. There will be I was a late bloomer, so I was awful. I scraped through school, I scraped through university, and actually once I left formal education, that's where all of a sudden I became really hungry to learn. And so I was a late bloomer. And so it's about having opportunities, whether you want to go through university or whether you want to go through apprenticeships. But there will always be an opportunity to teach yourself or to go and educate in some establishment. The important thing is that hunger. The important thing is never to believe that anything stops you. So do not be limited by anybody else. If you think that you can do it, and don't be scared to invent the future. Prediction of the future is pointless. What you can do is invent the future, and you do that by going, what do I think is going to happen? What do I want to enable? How do I break it up into individual steps? And then how do I sell those steps to people who might invest in that? How do I make those steps have value, inherent value for whoever's going to give me the money? And it's moved away from just massive organizations. NASA are not the only people that can put people into space anymore. Everybody, if you've got a good enough idea, there's research funds out there, and you can help to change the way that we become a spacefaring species.
Yeah, definitely. I think it's out there, isn't it? It's there for everyone to get their hands on. You mentioned you kind of scraped through university. Do you think your career would have been different if you hadn't gone to university? Do you think your passion for like energy, your passion for doing something new would have kind of come through?
Looking back on it, at my age, if there had been an apprenticeship scheme, for instance, that the United Kingdom Atomic Energy had, I would have been far better going into an apprenticeship scheme. That is exactly produces a quality of person exactly the same as if you went to university. So again, it's not about, there's always an opportunity to learn. It needs hunger, but because people take different times to mature, having people that go into education first and then get work experience, or in the apprenticeship you get work experience and then you educate yourself, having those two methods. However, I've always been confident that I could, it's down to me to make my own decisions. And I've always been hungry to learn. I love building stuff. So whether that is a fusion powered spacecraft or building a set of shelves in the study, I like building things. And so I was always going to do it in some format.
Awesome. No, that's great. There's actually a question coming in live from Mark. We're kind of coming back to the fusion and fission side of things and power systems. Is what are the risks? And Mark is asking, what are the risks of accidents occurring?
Yeah. So it is certainly a challenge. However, we are already, there is a significant work being done both in the UK and in America of how to create a fuel which is in an inherently safe lattice. We are creating structures and materials now which are have far higher impact resistance for things like kinetic energy, so explosions, for instance. And we have a lot of experience of transporting radionuclides around the world already. So yes, we need to make sure that safety is integral for a nuclear future in space. However, I think there are technologies and safety systems that already in place where nuclear systems would be able to survive a rocket explosion. So for instance, if you think about how we launch humans into space, we have them sitting on top of a rocket, and their part of the spacecraft has a way of ejecting away from the larger rocket. So even you could technically do the same thing with a nuclear reactor, but between materials, between the fuel itself, and between spacecraft safety systems, I see no reason why you would have large scale issues from some form of explosion or of the spacecraft which was carrying a nuclear core.
Yeah, I mean that's in terms of spacecraft. What about down here on like Earth? What do you think are the biggest obstacles until we start commercially using nuclear power?
So obviously on the fission side, I think fission. So you're terrestrially, we need a broad energy portfolio. We have to get rid of fossil fuels. So the clear and present danger to us all is climate change, and that is it. That is all we can think about. And to get rid of, to have a chance, we must get rid of fossil fuels as soon as possible. Renewables, although could provide a significant fraction of the energy needs, because of the temperamental nature of renewables, we need a really stable baseload, and that baseload must come from fission initially, and with suitable funding, fusion. And I think that if we had enough funding in fusion, I can see 2040, 2045 to be able to get some form of energy on the grid. enough to be able to say, okay, now we can get going. And so terrestrially, nuclear, however, whatever the nuclear legacy is, we have that nuclear legacy. We've had it since the 50s and 60s. The clear present danger currently is climate change. It's not the nuclear legacy, because we deal with that daily. So you've got no choice. You've got to put your money into nuclear and renewables to have a broad energy and a sensible energy portfolio in order to be able to get rid of fossil fuels as quick as possible. So, I mean, for me, the most fossil fuels are the most amazing product. So they are these really high energy density, and we set fire to it.
Yeah,
it's bonkers. Why are we setting fire to this miraculous product?
Yeah, I think it's something. Well, estimates show we have about, I don't know, 150 years of fossil fuels left, or between 50 and 150 years left, which is absolutely crazy. And the fact that we only started using it a couple of hundred years ago.
And it skews everything. So plastics are remarkably useful products. Unfortunately, the word plastic has now got this really bad image because we waste plastics on single throwaway stuff when you just don't need to use plastic there. We should be using our fossil fuels on plastics that last for a long time to fit a specific purpose.
What would you define as a long time?
So there are certain, so for instance, if you look at I'm saying that because I can see my monitor. If you look at your monitor screen, of course we could, of course. So your water bottle is a great example of this. So if your water bottle lasts for several years, then you have a good container. Now, if that was, and I've been guilty about this for, being so old, you buy a bottle of water from the shop, and then you've got this piece of rubbish. So it's about, can I reuse this? Will it hold its purpose for the longest period of time? And use those fossil fuels appropriately, because they have finite lifetime.
Yeah. Well, where do you think the shift comes then? Like, when do we stop? How do we force these massive companies to stop using fossil fuels? Because I think as individuals sitting at home, we're like, okay, I'll use a water bottle that lasts a couple of years, or I'll take reusable plastic bags next time I go shopping. But you're making a micro impact in the big.
Yeah, I mean, unfortunately, it normally is down to the way that money flows. So it will get to a point, and this is the unfortunate bit, it will get to a point where actually creating plastics will become really expensive, and a change will be forced. What would be really good is if governments launch some form of incentive scheme. And so what I would mean by that is, can you imagine that if I as a company produce a sustainable product, something that lasts either a long time or has low ecological impact, imagine getting a tax break. So what you need to do as a government is incentivize companies and organizations to have the best ecological impact, and do that via profits. That's the best way to do it. So make it expensive to have throwaway products. Give people money and tax breaks and whatever you have to do. If you make a television that can be repaired, give them a tax break. If I can swap the camera out of my phone and have a better camera on my phone without swapping the entire phone itself, give that company a tax break, because they've looked at how to make the best ecological impact on what is unfortunately a consumerist and capitalist society. We have to work within that framework.
That if there's something like that, That would be great because I'm sure there will be companies or entrepreneurs out there who are like, okay, well, one they're helping the environment, and if the government's incentivizing it, then it's a win-win situation for everyone.
Yeah, so I've always wanted to do it through the CE marking. So every product that we buy has to have a CE marking. It basically shows there's a level of safety. So therefore, every product has to go to someone to prove it's safe. Now, imagine that part of that CE marking was also the sustainability of that product, and somehow it provided information. So this is a good product. You will have these tax breaks, but if you used sustainable wood there, or you use this type of plastic here, you would get to the next tax bracket. Then this is, again, this is how do we incentivize? Not, it's really easy to build sticks. It's very hard to make carrots. So give people incentives to do good and not just hit them with a stick.
Great, yeah. Well, let's hope people are listening. And what do you finally, just, I know we've gone over time, and if you're still with us, thank you for tuning in. Just
sorry for rabbiting on.
No, it's amazing. I'm really enjoying it. Just one final question about the topic of nuclear waste, and I know lots of people have their own like weird theories about nuclear waste. But what are your views on like radioactivity?
So I think that there is a definite nuclear legacy, and that is something that we will be dealing with for centuries and longer.
Yeah.
Again, I think there is a clear and present danger of climate change, but we are, as a species, we have the potential to be ever so clever, and so there are a number of studies on how to try and reduce the activity and the half-life of some of so change the radionuclides so they have shorter half-lives by some form of transformation. But also, if you take, for instance, the work the University of Leicester are doing, they're looking at using americium in their RTGs. So not only will we not be spending money on looking after the americium, people will be paying us to take the americium away and then launching it into space. So you make money in a number of different ways there. We are getting rid of some of the long-lasting legacy. We're selling it as a product, and we're getting rid of it away from the planet. So again, it's about, we just need to be clever and need to work out and be invested in finding solutions to deal with these things, because it happened before I was born. We have this legacy from the 50s and 60s, late 40s all the way to the 60s, and so we just needed to deal with that, and we need to use ingenuity to deal with it.
Great, awesome. Well, thank you for kind of such an incredible talk. It's been a pleasure speaking to you, David, and thank you to everyone who's tuned in on YouTube. Thank you for your questions. I guess on a final note, kind of what do you think are the most positive signs like in nuclear power, and what kind of future power systems are there to look out for in the next 10 to 50 year period?
So at the United Kingdom Atomic Energy Authority, the STEP program, which is a £220 million program, looking for the UK to be the place to produce the first commercial reactor, is incredibly exciting. The UK is slightly biased, but the UK is one of the best places for fusion research. The government has backed UKAEA. UKAEA want to bring in SMEs, UK PLC to be the place for fusion energy in the world. Incredibly exciting. I think space-based solar power is also as another method for terrestrial energy is incredibly exciting. not only for the power itself, but how to build massive spacecraft in space, how to do in-orbit servicing and maintenance. It's incredibly, that's exciting as well. And of course, in about 4 or 5 years, we're going to go back to the moon. That's just going to be, I'm taking a few days off. I'm going to have a bottle of wine and I'm going to sit and watch that. That's what I'm going to do.
That's a great idea. That's a
yeah. It's that. So this is, I think, with both space and energy, this is one of the more exciting times that you can be alive. So yeah, it's great.
Awesome. Well, let's hope that we're out of a lockdown and we're back into our places of work very soon.
Yeah, absolutely.
Awesome. Well, thank you so much for giving an incredible talk. I've really enjoyed speaking with you, David. If you're still here on YouTube Live, thank you for tuning in. If you're watching this on Catch Up, don't forget to give us a big thumbs up and subscribe if you haven't already. We'll be back next Thursday, same time, 7 p.m. with another incredible space talk. But before that, on Tuesday, we're going to be live again with our space roundup, where we bring you the latest and greatest of space news. So tune in for that at Tuesday at 7:30. But until then, take care. Have a great weekend. Thank you so much, David. It's been a pleasure having you on the show. I hope you have a good weekend, and thank you for tuning in.